Hi everyone. Today I will be talking about buffers, their chemistry, and their importance in the real world. Specifically, I will be focusing on their use in cosmetics. The modern beauty industry is worth $532 billion, with skincare making up 39% of the global market. Clearly, cosmetics are all around us, but did you know that chemistry plays an extremely prevalent role in ensuring that these products are safe for our skin? They fulfill this purpose through their use of buffers. Buffers are solutions that maintain constant H+ concentrations and thus resist changes in pH. As a refresher, pH is the power of hydrogen, which measures how acidic or basic a solution is. A solution with a pH below 7 is considered acidic, while a solution with a pH above 7 is considered basic. A solution with a pH of 7 is neutral. When a weak acid and its weak conjugate base are combined in solution in approximately equal appreciable amounts, a buffer is formed. The same holds true for a weak base and its weak conjugate acid. Because of their composition, buffers can maintain the pH of a solution as the weak acid neutralizes the hydroxide ions when a small amount of strong base is added, and the conjugate weak base neutralizes H+ ions when a small amount of strong acid is added. These buffer systems are extremely important for vital processes and reactions that need to occur in certain stable pH ranges. For instance, enzymes function in optimal pH ranges, and if the environment strays from this pH, the protein will denature and no longer work. The blood is an example of a vital biological buffer system of carbonic acid and bicarbonate, with the purpose of maintaining the pH between 7.35 to 7.45. In this video, I will be exploring a non-biological example of a buffer system, phosphoric acid and the dihydrogen phosphate ion. Phosphoric acid is a weak acid, meaning it partially ionizes in aqueous solutions. But before we get started, it is important to understand what equilibrium reactions are. When a system reaches equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So no net change is observed, and the concentrations of the reactants and products remains constant. Now let's dive into the chemistry aspect of this buffer system. When placed in water, the buffer undergoes the following equilibrium reaction. Phosphoric acid and water are in equilibrium with hydronium ion and dihydrogen phosphate with little dissociation. The H3O+ is included because the dissociation of phosphoric acid will produce dihydrogen phosphate and hydrogen ion. The hydrogen ion is immediately attracted with the water molecule, forming hydronium ion. As previously mentioned, phosphoric acid is a weak acid, and dihydrogen phosphate is its weak conjugate base. When appreciable amounts of phosphoric acid and dihydrogen phosphate ion are combined, a buffer is made, which resists changes in pH. This buffer is an acid buffer, neutralizing small quantities of strong base to maintain the pH below 7. Its buffer range is 1.16 to 3.16. Equilibrium is present in the buffer system as phosphoric acid would constantly be dissociating into H+ and dihydrogen phosphate within an aqueous environment. At the same time, these ions would constantly form water and phosphoric acid. When a strong base such as sodium hydroxide is added to the buffer system, the phosphoric acid will donate its H+ ions to the OH-, converting the base into water and dihydrogen phosphate. Thus, the equilibrium is shifted to the right, following Le Chatelier's principle where the system's equilibrium position shifts to act against the disturbance of its equilibrium. When this shift occurs, the conjugate weak base is formed because the product side of the reaction is favored. The phosphoric acid in this reaction consumes the additional hydroxide ions, while the formation of the weak base ensures that the pH of the system does not fluctuate significantly. The amount of phosphoric acid lowers, while the amount of dihydrogen phosphate rises. Thus, the chemical equation of this reaction is as follows. Phosphoric acid and hydroxide ion react to form dihydrogen phosphate and water. But what about if we add a strong acid, such as hydrochloric acid, to the buffer system? Once again, Le Chatelier's principle is at play, shifting the equilibrium position to counteract the disturbance of the system's equilibrium. In this case, the equilibrium position will shift to the left, favoring the reactant side. Hence, a reaction will take place between the dihydrogen phosphate and the additional H+ ions of the hydrochloric acid, forming phosphoric acid and water. This reaction is as follows. Dihydrogen phosphate and hydronium ion react to form water and phosphoric acid. The change in pH is insignificant because the H+ is consumed by the dihydrogen phosphate ions rather than reacting with water to form hydronium. You might be wondering, where do we find this phosphoric acid and dihydrogen phosphate buffer in real life? Well, this buffer system is extremely important in skincare products. The skin's optimal pH is 5.5, as this pH ensures ideal protection against bacterial infection. This organ forms the external surface of the body that will be exposed to the environment, including all of the bacteria within it. These bacteria thrive in alkaline environments. So, by maintaining the pH of the skin to be acidic, meaning below 7, we can limit the growth of bacteria on the skin and thus prevent infection. The purpose of including buffers in makeup is to maintain the skin's acidic pH or to regulate the pH back to normal when it is not optimal. Without buffers, makeup is often quite alkaline, diminishing the skin's acidic protection and increasing one's susceptibility to disease. However, the use of buffers will resist the skin's change in pH with cosmetic application to provide maximum resistance against bacterial infection. Your next question might be, where else do we find buffer systems? Well, fun fact, buffers are also used in shampoo. A citric acid and sodium citrate acidic buffer is used to maintain the pH of shampoo below 7. This is important because the alkalinity of the soap within shampoo can immensely damage your hair, so the buffer helps to neutralize some of that alkalinity. Buffers are also used in baby lotion with a similar purpose as the buffers within cosmetic skincare products. When applied to the baby's skin before their diaper is put on, the acidity of the skin is maintained because of the buffer, thus obstructing bacterial growth within the diaper as these bacteria thrive in basic environments. At the same time, diaper rash is hindered. Buffers are also used in the brewing of alcohol. Before fermentation, buffer solutions are poured in order to maintain the pH so that the alcohol doesn't spoil. Ethanol used in alcohol is produced by yeast, and these microbes only function to ferment sugar and produce ethanol as a waste product in certain pH ranges. So, it's important that the optimal pH of the environment is maintained so that the yeast can produce the ethanol that alcohol requires. Overall, buffers are extremely important and prevalent not only within biology, but also in the industry. Without these systems, many reactions could not be undergone, numerous products could be very damaging to our skin, such as skincare products, some products would not exist, such as alcohol, and we would not be alive today without vital buffers such as that of blood plasma. Thank you.